Welcome back. This video is going to be on position, velocity, acceleration vectors in 2 and 3 dimensions. Not a lot new, it's just how we describe the standard kinematic quantities in more than one dimension. Here's our standard kinematic quantities. In one dimension, we use x for position, delta x for displacement, v for velocity, a for acceleration. In 2 or 3 dimensions, r is how we denote position, delta r is the change in position or the displacement, v and a still represent acceleration. And then in unit vector notation, it's the x component of the position times the I hat, y component times j hat, plus z component times k hat. And displacement is the delta x I hat, delta y, j hat, and so on. Velocity and acceleration follow the same process of identifying the unit vector notation. Now here's a sample problem. We have a position of a particle. It's given by this function. It's written in unit vector notation, and we want to derive the velocity and acceleration vectors for this particle. And then the question is, what does this motion look like? So going from the vector to what the motion actually looks like. So this position vector is a function of time, and if I want to find velocity, I have to take the derivative of the position function to find the velocity function. So we take the derivative of each component function independently, and that goes along with its unit vector. So velocity as a function of time. Okay, so the I component, we take the derivative of 80 plus 2t with respect to I, and that would just be 2i. And then we take the derivative of negative 40 with respect to t, and that would be 0j. And then our z component, we take the derivative of 5t squared with respect to t, and that would be, let's see, 10t. And it's negative. So it's going to be, let me correct that, it's going to be negative 10t in the in the k direction, sorry. The z component is negative 10t in the k direction. So that's a velocity. The next question is, what's the acceleration vector? Well, acceleration is the derivative of velocity, or the second derivative of position. So we just take the derivative of each component again. So the derivative of 2 is 0i. The derivative of 0 is still 0. And then the derivative of negative 10t is negative 10. And k hat. So the final question was, what does this motion look like? Well, if you look at our acceleration, this is constant acceleration, and it's accelerating negative k. If you remember, the standard three-dimensional axis looks like this. So it means that it's accelerating towards the xy plane at 10 meters per second squared. This kind of looks like two-dimensional motion with a free fall component. Interesting. Different way of looking at a problem that we're familiar with. Okay, so I'm going to do part A, and then you can do part B and part C. Okay, so we want to determine the velocity function. We have a position function with respect to time, r, is equal to the x components function times I hat plus the y components function times j hat. And here's x as a function of t, and here's y as a function of t. So we're going to follow the same process as we did in the last example problem. Okay, I'm going to take the first derivative of x with respect to t. So that would be 3t squared. The derivative of negative 6 is 0, and this is I hat. This is velocity as a function of t. And then the y component, we take the derivative of 5t minus 3 with respect to t, and that would come out as 5j hat. So that's our velocity function, and that should help you with the next two parts. Good luck, and we'll see you next time.